Alrighty, so today I'm going to be going over case study one, predicting employee attrition at Frito-Lay, presented on behalf of DDS Analytics by myself, Nicholas Jones. And first off, I just want to go over some qualitative analysis, get an idea of what we're trying to do, what the models that we'll be seeing they're trying to predict, and they're trying to predict attrition, which basically means a yes would mean that the person did leave the company, and missing out on employees who actually leave the company year in and year out can be highly costly for any company. So we're going to be looking at two main variables to validate the models. Sensitivity would be the predicted value of no attrition, meaning they did not leave, divided by the actual no attrition. Specificity would be the predicted value of yes attrition, meaning they did leave, divided by the actual yes attrition. Alrighty, so first off, I just want to go over some methods that I use to scan through the variables and see which is significant in predicting the attrition variable that we're trying to predict to prevent people from leaving the company. And as you can see, I have the p-value and whether that variable was significant in its independent analysis using the chi-square analysis for the categorical variables. These are all categorical variables, meaning they don't necessarily have a numeric output, even though there might be a number as the output. It's more so a level-based variable. And so as you can see, here's the equation for chi-square. X squared would be chi-square in this equation. O equals the observed, and E equals the expected. Now for the numeric variable outputs, output or the variables with numerical outputs, you ran a t-test. The null hypothesis would be that the same mean is just as likely to predict those who leave as those who will stay. So basically, if the output was essentially the same and you could not tell whether they were going to leave or whether they were going to stay, then it's basically a coin toss. It's not very useful, so that would be an insignificant variable. So you can see I had the same thing, whether that variable has a significant independent relationship with attrition or not, and the p-value that coincides with that, how significant that relationship is. And this is a overview of all of the variables that are close to or are significant, have a significant relationship. And as you see, the categorical variables kind of are heavily weighted towards the top right here as some of the most significant variables within the data set. The top five variables, which I'll be using for the following model, are overtime, stock option level, job role, job involvement, and job level. Alrighty, so for the first model output here, we had the original threshold, which was zero point 0.5, and then the optimal threshold, which is 0.18, which essentially moves the threshold in which something is denoted as yes or no within the data set. And this allows us to capture more at-risk individuals than the original threshold had modeled. I think the original specificity, which would be the at-risk individuals of leaving, was around 58%. Alrighty, so this is the final naive Bayes model. The top matrix would be the model after threshold fitting. The bottom matrix would actually be the model before threshold fitting. And as you can see, the model after threshold fitting allowed for more yeses to be predicted, and those yeses turned out to be actual people who were going to leave. So the specificity goes up at the sacrifice of a little bit of sensitivity. The sensitivity being the nose, but this is a good sacrifice for this model as we're trying to achieve a minimum of 60% on both of these variables. So here's the area under the curve and the threshold for the KNN model. The original threshold again was zero point 0.5. The optimal threshold for this model was 0.216. And this allowed us to capture many more at-risk individuals originally, this model actually was heavily weighted towards sensitivity. So here's sort of a reiteration through the matrix output of the KNN model so we can get an idea of how the model looked before the threshold fitting and how it looked after the threshold fitting. So the top matrix will be the model after the threshold fitting, and the bottom matrix would be the model before the threshold fitting. And so essentially we can see that the model before the threshold fitting was predicting a lot less guesses. And so that was the main goal of sort of changing the threshold, is so that the model would accommodate for more yeses, because those are the big costs at the end of the day. And that helps us get within that 60% specificity and 60% sensitivity. Alrighty, so this is the bottom line. This is the main reason why we ran these models. This is what we were trying to do. So I have a little bit of a legend to the left here, but the main idea of the models is that we saved $393,600 with the naive Bayes model, and that's per 30% of 891 observations. This is the test set that we were testing on. 30% of the observations that we were given. This is how much we saved. And with the KNN model, we saved $185,200. Thank you for listening to me today. My name is Nicholas Jones. Here's my email. You could contact me at nickjones@smu.edu. Here's some citations if you would like to go over those. Thank you and have a great day.